In this presentation, we will discuss the anatomy of foreskin, the effects of pressure on blood flow, and the stresses created by the Gomco clamp, in an attempt to create a basis for understanding the source of bleeding and the relationship between clamping pressure and blood flow. Foreskin is a mucocutaneous tissue comparable to the eyelids, lips, and anus, which acts as a boundary between the mucosa and skin. It is made of 5 layers: squamous mucosal epithelium, lamina propria, dartos muscle, dermis, and outer glabrous. Both the inner layer of the foreskin and the glands of the penis are composed of the same squamous mucosal epithelium. Langerhans cells found in the inner lining of the foreskin take foreign bodies and present them to the immune system. This is one way the foreskin aids in the transmission of the HIV virus. In other areas of the body, this type of skin contains melanocytes, which produce melanin, but they are not found in the foreskin. As a result, the inner lining of the foreskin lacks any pigments to change its pinkish color. The lamina propria is a thin layer of vascular connective tissue that contains an array of blood capillaries. These capillaries are the primary source of bleeding associated with circumcision if hemostasis isn't achieved. Glands that supply the mucosal epithelium with immune cells and mucus are located within the lamina propria. This tissue can be found in all mucous membranes throughout the body. The collagen is looser in this tissue than the dense lamina propria found in the glands of the penis. This increases the chance of bleeding since collagen is required for coagulation. The middle layer, the dartos muscle, is a layer of muscle that separates the 2 main layers of skin. It is made up of smooth muscle cells and elastic fibers. This allows for changes in volume with changes in temperature. Nerve bundles run along either side of the muscle. It should be noted that the ratio of muscle to elastic fibers decreases with age. The dermis is mainly connective tissue, blood vessels, and nerve bundles. There are more elastic fibers than in the lamina propria, which allows the foreskin to fit around the glands and helps it to reposition. The outer epithelium is formed from stacks of keratinized cells which die as they move up the epidermis until the outermost layer, which is all dead skin cells that protect the rest of the layers from external factors. While there are still Langerhans cells in this layer of skin, they are much less dense than in the inner mucosal epithelium. It should be noted that there are melanocytes present in this layer, responsible for this layer being pigmented. Nerves run through each of the layers of skin. In the foreskin, there are an increased number of encapsulated receptors, resulting in a high sensitivity in this region. Bleeding after a circumcision has been performed is evidence of incomplete clotting. The lamina propria and subcutaneous tissues in the layers of the foreskin contain loose collagen, which make clotting difficult. As a result, the amount of pressure and clamping times are critical. The clamping pressure will now be analyzed in detail. When the skin is subjected to pressure, the blood vessels are crushed. This causes internal bleeding, and the body responds with hemostatic mechanisms. After a short period of time, blood clots are formed and the internal bleeding stops, creating a seal that will temporarily prevent blood flow when the skin is cut away. The pressures required to stop blood flow have been found experimentally for various circumstances. The minimum pressure needed to cause the necessary seal is slightly under 1 psi. In a study involving the effects of pressure on blood flow in nerves in a rabbit, 8 psi was applied for an hour, resulting in no blood flow through the nerve for over a week. The industry standard when it comes to circumcision clamps is the Gomco clamp. The forces that are generated when the foreskin is crushed between the bell and the anvil generate a large amount of stress. The next slides contain a detailed analysis of the stresses generated in the skin when the clamp is used. In order to quantify the stresses the skin experiences, the bottom of the plate of the clamp will be the focus of the analysis. The bottom plate is highlighted here. The anvil is the only part of the plate in contact with the bell. The anvil now needs to be examined more closely. If a section view is taken of the base plate, the anvil geometry is revealed. The anvil is a very small machined land which can be seen if the anvil is enlarged. However, because the anvil itself is a flat surface, the stress distribution will be constant across it. The edges of the clamp create stress concentration in the skin by nature. If the edges are magnified, there is a slight radius that can be seen. Since the edge of the clamp is radiused, it can be modeled in a simple fashion. With the radius on the edge of the anvil known, the clamping surface can be idealized as a cylindrical indenter. Essentially, the edges are modeled alone, neglecting the middle of the anvil where the stress is known to be equally distributed and of lesser magnitude. A 2D approximation can now be used for analysis. A cylindrical indenter is a classical problem in solid mechanics. However, in this case, the indenter is in contact with skin. The skin will be modeled as an elastic half-space in order to account for its unique properties. The skin distribution is shown where 2b is the contact area and b over delta is the depth of the stress into the skin. The coordinate system defines z as perpendicular and x as parallel to the skin. The origin will be the center of the stress distribution. Based on the loading, it is apparent that the skin will fail in shear. Because of this, the maximum shear stress needs to be calculated. This can be calculated using Moore's circle once the normal stresses sigma xx, sigma zz, and tau xz are known. The equations used for this are displayed. They are functions of numerous variables defined in the next few slides. The variables used in the previous equations are defined in detail here. All the known constants are listed as well as the two independent variables x and z. Since the equation is a 2D model, the input requires two independent variables. The coefficient of friction used is for skin on steel, a close approximation given the construction of the Gomco clamp. The equation for maximum shear stress is shown. Using the known constant values and an applied force of 1, a baseline max shear force can be calculated. This value can be divided by the allowable shear to develop a multiplying factor. This factor can be used to calculate the maximum allowable applied load, since the equation is made up of many long, tedious components. A MATLAB script will be used to evaluate the equation over a given range of x and z values. This graph displays equation 1, evaluated with an applied force equal to 1 pound force and a contact area of 6/1000th of an inch. A maximum shear stress stands out. Let's take a closer look at the peak. When the shear stress is examined in reference to the x direction, the maximum value is located 6/1000th of an inch from the origin, or at the edge of the contact area. If we overlay the indenter model over this graph, the stress distribution becomes more intuitive. Because the indenter meets the skin at an angle on the Gomco clamp, the force has two components. One of the components pushes the skin in a positive upward direction. This causes the maximum shear stress to be on the positive side of the origin. The frictional forces also make the shear on one side of the indenter much higher than on the other side. These force components result in the uneven stress distribution within the skin. When the stress is looked at in the z direction, the trend is very obvious. As the value of z approaches 0, the shear stress approaches its maximum value. This means that the maximum shear stress occurs at the surface of the skin. This makes sense physically as well as analytically, since you would expect a tear to start at the surface. In summary, due to the crushing surface's unique geometry, it can be idealized as a cylindrical indenter in order to determine the shear stress distribution analytically. The maximum shear stress in the z direction occurs at the surface of the skin. Additionally, the maximum shear stress in the x direction occurs at the edge of the indenter, 6/1000th of an inch from the center. Finally, the maximum shear stress generated from an applied load of 1 pound force is 59 kips per square inch, or 406.8 megapascals.